Momentum is a measurement of a moving object's tendency to stay in motion. The equation for momentum is simply the mass of the object times its velocity. Frequently in MCAT problems, you'll be dealing with what's called conservation of momentum, which simply means that when objects collide, the total momentum in the system doesn't change. In other words, the mass times the velocity before the collision is going to be equal to the mass times the velocity after the collision. A boxer being punched in the face is an excellent example of momentum being conserved. Before the boxer on the right hits the gentleman in the face, his hand has momentum, and that equation is the mass of the hand times the velocity, and that's moving to the left. Once his fist hits the other boxer's face, his hand slows down dramatically. In turn, the other boxer is knocked back. And if we analyze the picture, we see a lot of movement in the boxer receiving the punch. His ears bend, his nose bend, his cheeks bend, and it appears they all go in different directions. If you add up the mass times the velocity of all the different parts of the boxer on the left, they would be equal to the initial momentum of the boxer's fist coming from the right. Or in other words, all of the red mass times the velocity is going to be equal to all of the blue mass times its velocity. In a way, a recoil problem is the exact opposite of a boxer being punched in the face, but the same principles of momentum still apply. We have a cannonball that's about to be fired from a cannon. Initially, there's no movement, so we could say the mass times the velocity is equal to 0. After the cannonball is fired, two things are happening. Obviously, the cannonball is moving very quickly to the right, so the cannonball has its own momentum. Also, the cannon is being knocked backwards. That's what we call recoil, and the mass times the velocity of the cannonball is going to be equal to the mass times the velocity of the cannon. Another way to look at it is like this. When the cannonball is moving to the right, we call that positive momentum. When the cannon is moving to the left, we call that negative momentum. So if we were to combine the two momentums of the cannon and the cannonball, preserving their positive and negative values, we'd find that momentum is conserved. In other words, the negative momentum of the cannon moving to the left, combined with the positive momentum of the cannonball moving to the right, well, that's going to equal 0. And 0 is the exact momentum that we began with. In other words, momentum has been conserved. It hasn't changed. Here's a simple recoil problem that's going to exhibit the exact same principles we saw with the cannonball and the cannon. Since we know that everything is going to be conserved and nothing's really going to change, we can just jump to the last step, and that is that the mass times the velocity of the bullet is going to be equal to the mass times the velocity of the gun. So in this case, we have a mass of 0.01 kilograms times a velocity of 300 meters per second. And we know that's going to be equal to the mass of the gun, which is 4, times a velocity that we don't know yet. Or 4 times the velocity of the gun is going to be equal to 3. Or the velocity of the gun is roughly equal to 0.75 meters per second. Here's a problem that's going to exhibit features of both the recoil and the collision aspects of momentum. So we have Jane and John, and they're 10 meters apart. Initially, we have Jane, and she weighs 40 kilograms, and she's going to throw a ball that weighs 1 kilogram. And the ball she throws has a velocity of 10 meters per second. This part of the problem is the recoil part. So we know the mass times the velocity of Jane after she throws the ball is going to be equal to the mass times the velocity of the ball after it's thrown. The mass of the ball is 1, the velocity of the ball is 10, and that's going to be equal to her mass of 40 times the velocity that we don't know yet. Or the velocity of Jane is equal to 1/4 of a meter per second. On the other side of the lake, we have Jack. Now Jack is going to catch the ball, and since when he catches the ball, he actually holds on to the ball, we could say that after he catches the ball, his total mass changes. So the problem gives us his mass as 59 kilograms, but once he catches the ball, his real mass is going to be 60 kilograms because he's hanging on to the ball. And the same rules of momentum apply. The mass times the velocity of the ball that Jack is going to catch, that's going to be equal to the mass times the velocity of Jack after he catches the ball. So the mass of the ball is 1, the velocity of the ball is 10, and that's equal to Jack's mass of 60 times his velocity that we don't know yet. Or his velocity is equal to 1/6 of a meter per second. Now we just use our standard velocity and time equations to figure out how far everyone has traveled in the 10 seconds. So the easiest equation to use would simply be that the velocity times the time is equal to the distance. Jane's velocity is 1/4. She travels for 10 seconds, which means her distance is 10/4 of a meter, or 2.5 meters. Since the ball has to travel 10 meters to John, and the ball is traveling at 10 meters per second, the ball is simply going to be in the air for 1 second, which means by the time that John catches it, he's only going to hang on to the ball for 9 seconds. So then we say John's velocity times his time is equal to his distance, or his velocity of 1/6 times a time of 9 seconds is going to be equal to 9/6 of a meter, or 1.5 meters. And then we just add everything up. The 2.5 that Jane traveled, plus the 10 meters the ball traveled, plus the 1.5 that John traveled. So John and Jane are 14 meters apart.